Dear students, I am going to prove Bolzano-Weierstrass theorem for sequences in this video. Now this theorem is actually a sufficient condition for the existence of a limit point. If this condition holds, then you can easily say that there is a limit point of the sequence. What is the condition? Every bounded sequence has at least one limit point. That means if the sequence is bounded, then definitely there will be a limit point. So every bounded sequence has at least one limit point. So if sequence is bounded, then definitely there will be a limit point. Fine, this is the Bolzano-Weierstrass theorem. So now you can see if sequence is bounded, this can be proved that if this is the sequence L, if this is the sequence 1, 2, 3, 4 and so on, sequence is bounded. If sequence is bounded, if the sequence AN is bounded, that means there exists a positive constant K such that AN is laying in between this. We have already know this. So here will be a K. This is positive K minus K. So all the terms of the sequence, they will be laying here. Maybe positive, maybe negative, we don't know, but all the sequence, all the terms will be laying here. Fine, this is the statement. And since so what is the range? Range is this. Range is obviously the subset of minus K to K. Fine, and this is nothing but a bounded set. So if sequence is bounded, this implies range set is bounded. If sequence is bounded, then range set is also bounded. And you can easily understand this. So this implies, so let AN be the bounded sequence and S be its range set. That S is nothing but collection of AN, because what is here? For example, here is A1. So this is nothing but your A1. This is your A2, for example. So this is your A2. So all the ANs is actually laying here. A1, A2, AN. These are all points. These are just the images. These are just the images of this on this axis. Fine. So that's why S is nothing but collection of all the ANs. So S is also bounded because sequence is bounded. So range set is also bounded. So AN is bounded. This S is bounded. So AN is bounded. Now here, depending upon the type of the sequence, S is finite or infinite. For example, suppose your sequence is N. Simply N. Then what is the sequence? Then range set is again 1, 2. This is now 1, 2, 3, 4 and so on. This is infinite. But second option is, if suppose we are having minus 1 raised to the power n, then we have 1, minus 1, 1, minus 1, 1 and so on, and range set will be minus 1 and 1. This is finite. So now we will take both these cases. So here first case, when S is finite set, that means we are taking this case where S is finite. Range set S is finite, here S is infinite. So here I am taking first this case. Fine. Then obviously, since S is finite, then there exists a real number L such that AN is equal to L for infinitely many values of N. Here for example, suppose L is 1 from here, then this 1 corresponds to all the even terms which are infinite. which are infinite. That's why if an equal to L in this case, then this correspond to infinitely many n. That means repetition. It's a case of repetition of an equal to L for infinitely n. And this is the example. Here 1 is repeated. 1, 1, 1, 1, 1. That's why it's a case of repetition. So that's why when you take any neighborhood, so in this case, if you take, for example here, if you take any neighborhood, 1 plus epsilon, 1 minus epsilon, then this neighborhood contains infinitely many terms, all the even terms. That's why here, so for any neighborhood, this contains infinitely many terms of an, and hence L is a limit point of the sequence. Fine. Now the second case, let S be an infinite set. That means now we are taking the first case. Here S is an infinite set. So since S is an infinite set which is bounded, then by Bolzano-Weierstrass theorem for set S has at least one limit point, say L. Then L is a limit point of this set S. That by the what is the definition? Every neighborhood of L contains infinitely many numbers or elements of S. Fine. But that means every element of here at this here contains infinitely many elements here in this range. But every infinite number here is nothing but a term of the sequence, because this is correspond to this, every element comes to correspond to a term of the sequence. That's why every neighborhood of L contains infinitely many elements of S, but each element of S is nothing but a term of the sequence. That's why every neighborhood of L contains infinitely many terms of the sequence, and that's why L is a limit point of the sequence. Fine. So this is the proof of this theorem. Now in the next video tomorrow we will prove few more theorems on boundedness of the sequence. Thank you.